Okay, for topic 6, we need to talk about the inverse tangent function. So hopefully we can kind of scoot through this one without doing some of the general background information, because at this point we've seen inverse sine, we've seen inverse cosine. Some of this stuff we're getting more comfortable with. Okay? So the definition here we say is if f of x equals tangent of x, then its inverse is defined to be f inverse of x equals inverse tangent of x. Okay, so that shouldn't surprise you. We had basically the exact same definition for inverse sine and inverse cosine. So just like with the other two, we want to look at the graph of just regular old tangent. Okay, so looking at this graph of tangent, we can see the vertical asymptotes, the x-intercepts. We can see that our range is from negative to positive infinity. We can see our domain is pretty wacky. Everywhere we have a vertical asymptote, we have an issue. So we can see here that our domain is everything except odd integer multiples of pi over 2. Okay, so we can see our domain and range very nicely here. The question is, okay, we know that tangent's a function. This for sure passes the vertical line test, but is it a one-to-one function? And the answer is absolutely not. Okay, so if we were to draw a horizontal line, we can see very easily that this horizontal line, just even on this, relatively this tiny little segment of tangent, we intersect tangent many, many times with this horizontal line. So this is definitely not a function. Okay. And so to answer this question over here, we can certainly say, no, it's not a one-to-one function. It's a function, but it's not one-to-one. And so the simple explanation is it fails the horizontal line test. And we know to be a function, each input has to correspond to only one output. So that tells me the input values can't repeat, but we don't really care about the output values. But when we're talking about a one-to-one function, we need a situation where each input corresponds to a unique output, meaning input values can't repeat, but neither can the output values. And because of the periodic nature of trig functions, they're always going to repeat those output values. So when you're talking about tangent, it has a period of pi. So no matter what value you have, so like if you're kind of imagine the unit circle, no matter where you're at on the unit circle, if you add or subtract pi radians, you're going to end up at another place that has the same exact output value. Add or subtract another pi radians, and you're going to end up somewhere that has the exact same output value. So these trig functions just kind of automatically are not one to one. So we could also say because tangent is periodic, output values output values repeat every pi radians. And remember, the period for tangent is pi, not 2 pi, like it is for cosine and sine. Okay, so this is definitely not a one-to-one function. So just like with sine and cosine, in order to define or have an inverse, we need to have a situation that is one-to-one, because we know if a function is one-to-one, it has an inverse that is also a function. Okay, so just like with sine and cosine, we're going to take a segment of tangent and we're going to define the inverse based on that restricted segment of tangent. Okay. Now, the good news is we're going to look at the segment from negative pi over 2 to positive pi over 2, which is really similar to sine. Not exactly the same, but very similar to sine. Okay. So that means if we're talking unit circle stuff, we're looking at that quadrant 1 and quadrant 4 as well. Now, here's the issue. At exactly negative pi over 2 and exactly positive pi over 2, can we be exactly those values? And the answer is no. Those are actually vertical asymptotes for tangent. That means at exactly negative pi over 2 and exactly pi over 2, tangent's not defined. So when we look at our restricted domain, it's not exactly the same thing as sine, okay? It's not going to include those endpoints. So if we look at the restricted sine domain, we were looking at negative pi over 2 to positive pi over 2 inclusive, meaning we could include those exact values. With tangent, we cannot include those exact values. So you want to use rounded brackets if you use interval notation. And if you use the like negative pi over 2 is less than theta is less than pi over 2, just make sure you use less than, not less than or equal. Okay? So to make tangent a one-to-one function, we restrict the domain. Historically, the universally agreed upon domain restriction is negative pi over 2 to positive pi over 2. So again, very similar to sine, but not quite exact, okay? Now, with that said, we're definitely looking at quadrants 1 and 4 on the unit circle still, okay? Now let's look at what the inverse tangent function is going to be, okay? So we're going to use this little snippet of the tangent function. So we're going to look at this graph, which is just a little snapshot of tangent. It's our restricted domain, okay? So notice we have our asymptotes. So the vertical asymptotes for this particular interval are negative pi over 2 and positive pi over 2. And remember, when you're dealing with a function and its inverse, if you take the function, like the graph of the function, and you take all the ordered pairs, you flip-flop the x and the y, you end up with the graph of the inverse. So we're going to kind of do that with these asymptotes. So our asymptotes are at x equals negative pi over 2 and pi over 2. So we're going to have this new situation at y equals pi over 2 and y equals negative pi over 2. We want to make sure our graph of the inverse tangent doesn't cross or touch these values. Okay? So we've taken care of that part. Now we need to come up with at least 3 other points on the regular restricted tangent function that we can then flip-flop so that we can get a graph of the inverse tangent function. So the first one, it's easy. It's just the origin. Okay, and that's just going to be the origin on inverse tangent as well. Now, hopefully you kind of remember there are 2 really easy points on the unit circle from negative pi over 2 to positive pi over 2, and those occur at negative pi over 4 and positive pi over 4. At negative pi over 4, we have a ratio, we have a tangent ratio of -1. So this ordered pair, negative pi over 4 comma -1, well, we can switch it a little bit. We can just flip-flop the x and the y, and that'll become, whoops. We can switch the x and the y, and -1 comma negative pi over 4 will be a point on the inverse tangent function, okay? Similarly, at positive pi over 4 radians, we end up with a ratio of +1. So at positive pi over 4, we have a tangent ratio of 1. Remember, that's where we have root 2 over 2 for cosine and then root 2 over 2 for sine. So that ratio for tangent's 1. So if we flip-flop that ordered pair, we would get 1 comma pi over 4, which will be on the inverse tangent function. So let's go ahead and start graphing this one, okay? So we know we have the origin. And then for pi over 4 comma 1, that's going to flip-flop to be 1 comma pi over 4. So let's say 1 is about here-ish, and then we've got pi over 4. And then negative pi over 4 comma 1 becomes -1 comma pi over 4 when we flip it. So we're going to get something around here that's kind of an eyeball. Okay, now if you look at these points, they look like they could be aligned, but remember, that is not what tangent looks like, okay? So I'm going to try my hardest. I have the absolute hardest time graphing inverse tangent. I don't know why. It's like a deficit in my brain, but I'm going to try really hard. Okay, so it kind of does something like this. And then, like, that's not the worst one I've ever drawn. It's not the greatest, but it's not the worst, okay? So this right here is the graph of the inverse tangent function. So this is the graph of the inverse tangent function. Okay, now let's talk about some important pieces of information from the regular restricted tangent to the inverse tangent function. So when we're talking about the domain and range for just the regular tangent function, we restricted our domain. Universally, we agreed that the domain for tangent, when we're in this inverse world, we would say the domain of tangent was going to be from negative pi over 2 to pi over 2. That's our restricted little like piece, our segment, our chunk of tangent, okay? Now the range is still negative infinity to positive infinity. You can see this graph goes forever in both directions, okay? Now let's look at the domain and range of the inverse tangent function. Well, when I look at the domain, okay, this graph goes forever in both directions, okay? So I would say the domain is negative to positive infinity, okay? And then my range, so if I'm going up, down, my range is negative pi over 2, comma, positive pi over 2, but I can't include either of those values because I have like an asymptote situation. So domain is negative to positive infinity, and the range is negative pi over 2 to positive pi over 2, not including the endpoints. And if you look at the tangent function compared to the inverse tangent function, the domain and range have flip-flopped, okay? Just please remember that when you're dealing with inverse tangent, the input is the ratio, and the output is an angle, but very specifically an angle from negative pi over 2 to pi over 2. Okay? And then don't forget, I have this right here. Notice the output of the inverse tangent function is an angle, and it has to be an angle from negative pi over 2 to positive pi over 2, just not including those endpoints, because remember, at those, excuse me, at those exact endpoints, tangent's not defined. Okay? Now, on the unit circle, remember that leaves us in quadrant 1 and 4, but be very mindful of how you get to quadrant 4. You cannot go through quadrant 2 and then quadrant 3 to get to quadrant 4. So you have to get to quadrant 1 from the positive x-axis going counterclockwise, and then you get to quadrant 4 from the positive x-axis going clockwise. So counterclockwise to get to quadrant 1, clockwise to get to quadrant 4. You cannot go through quadrants 2 and 3. Keep that in mind. Okay? Let's go ahead and fill in this table with the domain and range for tangent and inverse tangent. Let me get some water first. I have talked a lot today. Now, when we're talking about the domain of tangent, remember, we're talking about this restricted like segment of tangent. So keep that in mind. Okay. Now the domain, we have restricted it to negative pi over 2, comma, pi over 2. And then we decided the range was just negative to positive infinity. Now, when you're dealing with the range of tangent, that's going to be the same thing as the domain of inverse tangent. So the domain of inverse tangent is negative to positive infinity. I clearly forgot to type my little x here, so you can fill in that x there. I'm sorry about that. And then don't forget that the domain of tangent is the range of inverse tangent. So the range here is negative pi over 2 to pi over 2. And just don't forget when you're talking about the inverse tangent function, the input is the ratio, the output is the angle, as long as you're in that negative pi over 2 to pi over 2 interval. Okay, let's look at two examples. Now, I'll tell you, tangent can be a pain in the behind, all right? And it is a pain in the behind because when you're dealing with the unit circle, oh, that was a spider on my ceiling. When you're dealing with the unit circle, sine and cosine are just like on the unit circle. But tangent, you have to do that ratio of sine divided by cosine. So they can be a little bit harder to work with sometimes, okay? So for example 10, it says find the exact value of each of the following. And for part A, we have arc tan of root 3. Now remember, I don't think I reminded you of this at the beginning of this video, but if you have inverse tan, that is synonymous with arc tan. It's just a different notation, and don't be afraid of it. You'll for sure see it at some point in your calculus career, okay? So arc tan just means inverse tan, all right? So very, very informally, what this is saying is what angle from negative pi over 2 to pi over 2 has a tangent ratio of positive root 3. Well, we know that with tangent, we are restricted, okay? So we know with tangent, we are restricted to quadrants 1 and 4. Okay, well, tangent is positive, so tangent has those positive ratios in quadrant 1. So we can just forget about quadrant 4. That's not where this angle is going to live. It's going to be somewhere in quadrant 1. So let's kind of recreate quadrant 1. All right. So we have this first angle that gives us a cosine and a sine of root 3 over 2, comma, a half. And then root 2 over 2, comma, root 2 over 2. And then 1/2, comma, root 3 over 2. Okay, now one of these we can kick out immediately. All right, we can say without a shadow of a doubt, it ain't going to be this one. All right, root 2 over 2 divided by root 2 over 2 has a ratio of 1. It's never going to be root 3. Okay, so please do keep that in mind. Okay, so then it comes down to 1/2, comma, root 3 over 2 versus root 3 over 2, comma, 1/2. So which is it? Okay, so essentially we have to remember this one really, really important thing. We need to remember that tangent is equal to sine divided by cosine, which is y divided by x. So when we look at these ordered pairs, we need to figure out which y divided by x is going to give us the root 3, okay? So let's say we start with this first angle, okay? So we would have 1/2 divided by root 3 over 2 because this is our x, this is our y, okay? So that becomes 1/2 times 2 over root 3. So the 2's just divide out to be 1. So I get 1 over root 3. This ain't going to be it, y'all. So we want to go root 3 over root 3. We rationalize it. We get root 3 over 3. That is not root 3. So that tells me ain't this one. So by default, it has to be this ratio right here. And we can prove it to ourselves if we want to. We can say, okay, this time we have the y coordinate is root 3 over 2. The x coordinate is 1/2. Well, that's root 3 over 2 times 2 over 1. 2's divide out to be 1. So I'm left with root 3. That's the one. So the real question is, what is the angle? So what angle gives me that readout? And this is going to be pi over 3 radians. So the angle between negative pi over 2 and pi over 2 that has a tangent ratio of root 3 is going to be pi over 3 radians. So I would put pi over 3. Okay? Now, let's go over to part B and visit inverse tangent of negative root 3 over 3. So again, very, very informally, what this is saying is what angle from negative pi over 2 to pi over 2 has a tangent ratio of negative root 3 over 2. Well, if tangent's negative and we're restricted to negative pi over 2 to pi over 2, that means we have to be in quadrant 4 because tangent's positive in quadrant 1. So let's redraw quadrant 4. All right. So this point right here is going to have an xy point of root 3 over 2, comma, negative 1/2. This one is going to have a root 2 over 2, comma, negative root 2 over 2. And this one has an ordered pair of 1/2, comma, negative root 3 over 2. Okay, so we can kick out one of these right away. We know it's not going to be negative 45 degrees because, whoops, is that going to let me do it? All right, because that one has a ratio of 1. Now, if we go over here to the work that we already completed for part A, we know that when we have a y coordinate of 1/2 and an x coordinate of root 3 over 2, we get a ratio of root 3 over 3. Okay, so if we can find a situation where we have an x coordinate of 1/2, so this remember, or of root 3 over 2, so this is our y, this is our x. So if we have a y coordinate of 1/2 and an x coordinate of root 3 over 2, we get the right ratio, okay? So that tells me I'm looking at this angle right here. I want this one, okay? Because that has the right ratio. It has the negative 1/2 divided by root 3 over 3, or root 3 over 2, which is negative 1/2 times 2 over root 3. 2's divide out, which is negative 1/2 over root 3. If I rationalize, I very much get my desired ratio. Okay, so what angle is that? This is negative pi over 6. So I would say this right here is negative pi over 6. Okay, so that was a little long and drawn out, but there you have it. Okay.